Close your eyes for just a second. Imagine you're in a deep, dreamless sleep, totally unconscious to the world around you. Or picture being put under general anesthesia for a medical procedure. The lights are completely out, right? Your awareness is effectively turned off. So what exactly is your brain doing when you aren't looking? Well, for a really long time, the assumption was, honestly, not much. We kind of thought of the unconscious mind as a dormant machine, just quietly idling on standby. But what if I told you that behind that veil of darkness, your brain is actually engaged in a frantic, astonishingly complex symphony of covert activity? Welcome to This Explainer, where we're going to explore the awe-inspiring mysteries of the human brain. We're diving straight into modern neuroscience to uncover the secret operations of your mind. We'll look at the lightning-fast ways it rewires itself, its hidden activities when you're completely sedated, and even how its biological blueprints are literally inspiring the future of artificial intelligence. All right, let's dive into this. Section 1. The 100 billion neuron network. Before we can really understand how the brain learns or what it's up to in the dark, we have to establish the sheer scale of the biological hardware we're dealing with here. 100 billion. Take a moment to let that number sink in. That is the approximate number of neurons, those individual nerve cells inside an adult human brain. It's a number so large it actually rivals the stars in our galaxy. But it's not just the sheer volume of cells that makes the brain the most complex structure in the known universe. It's how they communicate, forming up to 10 quadrillion connections. Take a look at the basic anatomy of just one of these cells. You can see the main cell body, the soma, sitting right in the center, but check out those branch-like structures extending outwards. The ones pulling information in? Those are the dendrites, and they basically act as the cell's receivers. When a signal is received, it triggers this electrical pulse that ripples all the way down that long tail, which is known as the axon, to pass the message along. But here's the catch. When that electrical signal finally reaches the end of the axon, it doesn't actually physically touch the next neuron. Instead, it has to cross this microscopic gap called a synapse. And the brain bridges this gap using chemical messengers called neurotransmitters. These little chemicals are released from the first cell, they float across the gap, and then bind to the dendrite receptors of the next cell. It's basically a continuous electrochemical relay race, and it is happening trillions of times a second inside your head. Now, for the longest time, the prevailing scientific dogma held that once we reached adulthood, this incredibly dense, tangled forest of neurons was completely static. Back in 1928, Santiago Ramon y Cajal, who's widely considered the founder of modern neuroscience, stated that adult nerve paths were fixed, ended, immutable. Everyone pretty much believed that you couldn't grow new connections, and the brain you had was essentially set in stone.
Section 2. Rewiring after a single experience.
But as we know, science evolves. We now know the brain is absolutely not a static block of stone. It's more like highly moldable clay, continuously reshaping itself through neuroplasticity. But how exactly does it rewire? Well, in 1949, a psychologist named Donald Hebb proposed a theory that would dominate neuroscience for over 70 years. He essentially argued that when neurons are activated at the exact same time, the physical connection between them gets stronger. Hence the famous catchphrase, neurons that fire together, wire together. Researchers always had this sneaking suspicion that Hebb's theory wasn't the whole story, though. You see, traditional Hebbian plasticity requires neurons to fire within mere milliseconds of each other. And it usually requires an experience to be repeated over and over and over again. That perfectly explains how you slowly learn to play the piano. But it definitely doesn't explain how you learn not to touch a hot stove after a single painful fraction of a second. The brain clearly needed a way to capture experiences that unfold over several seconds, not just milliseconds. And recently, researchers made a massive breakthrough. A team led by neuroscientist Jeffrey McGee discovered a completely new type of learning called BTSP, or Behavioral Timescale Synaptic Plasticity. This is a powerful mechanism that actually allows the brain to completely rewire itself and form a memory from a single, quick event, stretching that window of learning from milliseconds to a span of several full seconds. Let's break down this rapid biological process, because honestly, it plays out like a movie. Imagine a mouse exploring a maze. First, as it moves, its active synapses are tagged with a biochemical marker, an eligibility trace. Think of it like a biochemical sticky note that lingers for a few seconds. Then, bam, a massive electrical surge called a plateau potential fires across the dendrite. Instantly, all those tagged synapses are strengthened in one swift, single step. The crucial takeaway here is this: one single burst of electrical activity can completely tune a brain cell to a brand new memory. Your brain doesn't always need endless, tedious repetition.
In literally a matter of seconds, your neural network can physically remold itself to adapt to a sudden realization or totally new environment. It is just an astonishingly dynamic machine. Section 3. Secrets of the unconscious mind. Which brings us to a really fascinating paradox. If our conscious brain is this active, what in the world happens when consciousness is completely turned off? A groundbreaking study from the Baylor College of Medicine recently tackled this exact question. Dr. Samir Sheath and Dr. Benjamin Hayden took advantage of this incredibly rare opportunity with patients undergoing epilepsy surgery. While these patients were fully under general anesthesia, meaning totally sedated and completely unconscious, researchers placed advanced neuropixels probes directly into the hippocampus, the brain's memory center. They then played audio of short stories to these deeply unconscious patients. The results challenge everything we thought we knew about consciousness. The completely anesthetized brain didn't just hear random noise. It actively processed the complex grammar of the stories. The neural recordings proved the unconscious hippocampus was actually distinguishing between nouns, verbs, and adjectives in real time.
But hold on, because it gets even wilder. The researchers found that the neural signals were actually predicting upcoming words before the audio track even played them. Really think about that for a second. The brain was acting as an active prediction machine, anticipating the future and decoding language, all while the patient was entirely unaware. Predictive coding isn't just a feature of active waking attention. It is a fundamental automatic function of the biological network itself.
Section 4. Brains versus artificial intelligence.
Now, if that idea of a network predicting the next word sounds a bit familiar to you, it really should, because this biological marvel has become the exact blueprint for our most advanced technology. Comparing the brain to a traditional computer brilliantly illustrates the vast differences between biological and traditional computing. Conventional computers rely on sequential algorithmic processing. They have incredibly fast clock speeds, running at billions of hertz, but they process things serially, just one step at a time. Your brain, on the other hand, operates at a much slower speed, maybe 100 hertz, but it has a massively parallel architecture. Millions of paths are firing simultaneously. This makes the brain incredibly fault-tolerant. If one neuron dies, no big deal. The network adapts and routes right around it. But if you remove just one transistor from your laptop CPU, the whole machine crashes. Because traditional algorithmic computers struggle with the messy, unpredictable reality of the world, computer scientists ended up turning to neuroscience for inspiration. Artificial neural networks were designed to directly mimic the distributed, interconnected, fault-tolerant architecture of the human brain. Instead of writing rigid line-by-line rules, programmers build artificial nodes that represent biological neurons, allowing the system to learn by example, adjusting the weight of its digital synapses as it goes. This brain-like intelligence bridges a really crucial gap. Ask a traditional computer to calculate the square root of a massive number, and it knocks it out in a millisecond. But ask it to recognize a picture of a cat or read messy human handwriting, and historically, it completely failed. But by using artificial neural networks, by literally copying the biological structures we've been talking about today, AI can finally perform these complex pattern recognition tasks that we humans find so effortlessly easy. If you take one thing away from this explainer, let it be this. Your brain is far more dynamic, capable, and mysterious than we ever gave it credit for. It is deeply plastic, capable of physically rewiring itself in mere seconds through single-shot learning mechanisms like BSTSP. Furthermore, this processing power never truly sleeps. Even when you are totally unconscious, your brain is actively parsing grammar and predicting the future. And finally, this elegant parallel biological web is the very foundation upon which we are building the future of artificial intelligence. Which leaves us with a pretty provocative thought. If a completely sedated, unconscious brain is perfectly capable of listening to a story, categorizing the verbs, and predicting the very next word, what exactly is conscious awareness? Is consciousness just an illusion, a byproduct of broad communication across different networks in the brain? Or is there something more? It's a profound question that challenges our very definition of what it means to be awake, and it's a mystery we'll just have to tackle in our next explainer. Thanks for learning with me today.